Welcome to Module 11, IPv4 Addressing. This is the subnetting capstone, the biggest, most math-heavy module in the course. Set expectations early. It builds directly on Module 5's binary/hex work and Module 8's IP addressing basics, and it moves slower than other modules. Budget extra time on every tip and trick slide. Objective: calculate an IPv4 subnetting scheme to efficiently segment a network. Preview the long topic list on screen. Address structure: unicast/broadcast/multicast. Address types: network segmentation, subnettings 24/16/8, subnetting to requirements, VLSM, and structured design. This module builds in layers, so don't skip ahead. Every IPv4 address splits into a network portion and host portion. All devices sharing a network must match on every network portion bit, while the host portion must be unique per device. Walk the binary breakdown on screen for 192.168.10.10, showing exactly where the network bits end and host bits begin. An IP address alone isn't enough. It needs a subnet mask paired with it to mean anything. The IP address identifies the specific host. The subnet mask identifies which bits of that address are network versus host. Show the Windows TCP IPv4 properties dialog on screen as a real-world reference point for where these values actually get entered. Prefix length / notation is shorthand for a subnet mask. Just count the 1 bits and write it after a slash. Walk the reference table on screen, 8, 16, 24, 25 and their corresponding dotted decimal masks. 192.168.10.10 with mask 255.255.255.0 becomes 192.168.10.10/24. Much easier to write and say out loud. Direct callback to Module 5's powers of 2 sequence: 128, 192, 224, 240, 248, 252, 254, 255. That's not a coincidence. Every possible subnet mask octet comes from exactly that progression. You will never see a mask octet, like 200 or 100. Have students recite the 8 values in order right now. Being able to read any mask on site saves huge time for the rest of this module. Logical AND is one of 3 Boolean operations, and it's how you find a host network address and the IP address with its subnet mask, bit by bit. Walk the truth table on screen. The result is only 1, true, when both inputs are 1. Applied across all 32 bits, this reveals exactly where the network address begins. Full worked example on screen: 192.168.10.10 ANDED with 255.255.255.0. Bit by bit yields 192.168.10.0. The rule to internalize: wherever the mask has a 1, the address bit passes through unchanged. Wherever the mask has a 0, the result is forced to 0. This is the mechanical process behind every network address calculation in this module. Every network has 3 key addresses, shown in the table for 192.168.10.0/24. The network address, ALL0 host bits, unassignable. The first host address, all zeros except the last bit. The last host address, all ones except the last bit. And the broadcast address, all 1 host bits, also unassignable. The number line diagram shows the usable range sitting strictly between the 2 blocked ends. Huge time saver. You never need to run the full AND operation just to find the network and broadcast addresses. The network address is always the first address in a subnet's block. The broadcast address is always 1 less than the next block's start. Drill this hard. If an exam answer assigns a device the network or broadcast address, that answer is always wrong. Unicast is 1-to-1, a single source sending to a single destination. The destination IP names exactly 1 recipient. Important detail: a source IP address can only ever be unicast, since a packet can only ever originate from 1 device, even if its destination is broadcast or multicast. Broadcast is 1 to all. Destination has all 1s in the host portion. 2 flavors, shown on screen. Directed broadcast targets all hosts on 1 specific network, like 172.16.4.255 for that 24. And limited broadcast, sent to 255.255.255.255, reaching every device on the local segment. By default, routers never forward broadcasts beyond the local network. Multicast is 1 to a group. Reduces traffic by sending 1 packet to only the subscribed hosts in a multicast group, rather than everyone. IPv4 reserves 224.0.0.0-239.255.255.255 for this. Real example: OSPF routers use the reserved multicast address 224.0.0.5 to talk to each other. Only OSPF-enabled devices even process those packets. Public addresses must be globally unique and are routed across the internet. Private addresses, RFC 1918, are reserved for internal use only, not unique, not internet routable. Walk the three private ranges on screen: 10.0.0.0/8, 172.16.0.0/12, 192.168.0.0/16. These were introduced in the mid-1990s, specifically to slow down IPv4 address depletion. Private addresses can't reach the internet directly. They need translation to a public address first, which is NAT's job, usually running on the router at the network edge. Worth flagging explicitly: the IETF doesn't consider NAT or private, addressing an effective security measure on its own, despite the common assumption that it is. Two special use address blocks shown on screen. Loopback: 127.0.0.0/8, commonly 127.0.0.1, a host testing its own TCP/IP stack. Any address in the block loops back locally. And link local, API-PA, 169.254.0.0/16. A Windows client self-assigns this when no DHCP server responds. The ping 127.0.0.1 screenshot is a quick way to demonstrate the loopback concept live. Historical context: RFC 790 in 1981 assigned addresses using fixed classes, deprecated by the mid-1990s in favor of the classless addressing used today, but the terminology still comes up. Walk the class A/B/C table on screen. Interesting fact worth mentioning: Class A alone accounted for half of all IPv4 addresses, with most going unused, since so few customers actually needed 16 million plus hosts. Public addresses can't just be picked arbitrarily. IANA manages both IPv4 and IPv6 address space globally, allocating large blocks to 5 regional internet registries, who then allocate smaller blocks to ISPs and large orgs. In practice, almost no administrator deals with IANA directly. They request space from their ISP, which already holds an allocated block. Broadcast problem, framed with the company-wide email analogy. On an Ethernet LAN, devices use broadcasts via ARP, DHCP to find each other, and switches flood those broadcasts out every port except the one they arrived on. This ripple effect is exactly why broadcast domain size matters for network design. A large broadcast domain means every device has to accept and process every broadcast packet, slowing the whole network and every device on it. Since routers don't forward broadcasts, they naturally separate broadcast domains. This is the direct motivation for subnetting. Breaking one large domain into smaller contained ones improves performance. Beyond just performance, subnetting also enables security policies, controlling which subnets can talk to which, and limits blast radius, fewer devices affected by a misconfiguration or malicious traffic. 3 common organizing strategies previewed on screen: by location, by group/function, or by device type. Each gets more detail in Module 11.9 later. Subnets are created by borrowing bits from the host portion to make more network bits. More borrowed bits means more subnets, but fewer hosts each. Easiest borrowing happens at octet boundaries: 8, 16, 24. Concrete example: a 10.0.0.0/8 network with 16.7 million hosts in one broadcast domain is unmanageable. Subnetting to 16 creates 256 subnets of 65,534 hosts each instead. Subnets don't have to stop at octet boundaries. Bits can be borrowed from any host position. Walk the full 24 reference chart on screen, 25 through 30, each with its subnet count and hosts per subnet. This chart is worth having students memorize or keep as a quick reference for the rest of the module. The 2 formulas that run this entire module worth writing on the board: subnets created equals 2 to the power of bits borrowed, borrow 3 bits, get 2 cubed equals 8 subnets, and usable hosts per subnet equals 2 to the power of remaining host bits, minus 2 for the network and broadcast addresses. 5 host bits left equals 2 to the power of 5, minus 2 equals 30 usable hosts. Every subnetting problem in this module reduces to these 2 calculations. Full worked example: 192.168.20.0/24 needs 8 subnets. Since 2 to the power of 3 equals 8, borrow 3 bits, giving a new 27 prefix with 5 host bits remaining. 2 to the power of 5 minus 2 equals 30 hosts per subnet. Walk the resulting subnet table on screen. Each subnet's block is 32 addresses apart, 0.0, 0.32, 0.64, up to 0.224, with the diagram showing 4 of these subnets assigned to real buildings. When more subnets are needed than a 24 can provide, start from a 16 instead. It has 16 host bits available to borrow from. Key detail: when borrowing from a 16, you start in the 3rd octet. Walk the full /17 through, 24/23 reference chart on screen. Same idea as the 24 chart, but scaled up. Concrete example. Subnetting the private 10.0.0.0/8/24 yields 65,536 subnets of 254 hosts each, popular because it lands cleanly on an octet boundary and gives a very manageable subnet size. Walk the pattern on screen. Each 24 increments the third octet by 1. Same 10.0.0.0/8 network, but subnetted at 16 instead, gives far fewer, far larger subnets, useful when 254 hosts isn't enough per subnet. 256 subnets of 65,534 hosts each this time. Point out the flexibility. A private 8 can be subnetted at 12, 18, 20, or virtually any length depending on the actual need. Worked example. An enterprise needs at least 100 subnets from 172.16.0.0/16. Test the borrow amounts. 6 bits gives 2 to the power of 6 equals 64. Not enough. 7 bits gives 2 to the power of 7 equals 128. Meets it with room to grow. New prefix is /16 plus 7 equals /23, leaving 9 host bits for 2 to the power of 9 minus 2 equals 510 hosts per subnet. Reinforce. When borrowing from a 16, work left to right starting in the third octet, 1 bit at a time. Similar problem. Bigger scale. An ISP needs 1,000 subnets from 10.0.0.0/8, 1 per client. Test. 9 bits gives 2 to the power of 9 equals 512. Not enough. 10 bits gives 2 to the power of 10 equals 1024. Meets it. New prefix, /8 plus 10 equals /18, leaving 14 host bits for 2 to the power of 14 minus 2 equals 16,382 hosts per subnet. Each client gets their own /18 block, more than enough to further subnet internally however they need. Most organizations use both public and private addressing simultaneously. 2 zones, contrasted on screen. The intranet, internal, private addressing, huge flexibility since private space is essentially unlimited, and the DMZ, internet-facing resources like a web server, public addressing, where address conservation actually matters. Every real-world subnetting decision comes down to 2 questions, shown on screen. How many hosts? The largest subnets requirement determines host bits needed, and how many subnets? The total count needed determines bits borrowed. These pull in opposite directions. More subnet bits means fewer host bits, since usable hosts is always 2 to the host bits minus 2. Full worked example. Corporate HQ has a public 172.16.0.0/22, 10 host bits, 1,022 addresses, needs at least 10 subnets. Largest subnet needs 40 hosts. Test subnet requirement first. Need 4 bits borrowed for 2 to the power of 4 equals 16 subnets. Covers 10. New prefix, /22 plus 4 equals /26, leaving 6 host bits for 2 to the power of 6 minus 2 equals 62 hosts. Comfortably covers the 40 host need. Both requirements verified in one pass. Strategy for picking the right prefix fast. Work from whichever requirement is given first, solve for that, then verify the other requirement still fits with what's left over. If given a subnet count, find the smallest power of 2 that covers it. If given a host count, find the smallest power of 2 minus 2 that covers it. Real problems often give both numbers at once. Exactly like the HQ example, always check both. The waste problem VLSM solves, 192.168.20.0/24, needs 7 subnets total, 4 LANs plus 3 WAN links. Traditional subnetting borrowing 3 bits gives 8 equal /27 subnets of 30 hosts each. Great for LANs, terrible for WAN links, which only ever need 2 host addresses. Walk the math on screen. 28 wasted addresses per WAN subnet, 84 wasted total across 3 links. VLSM, Variable Length Subnet Masking, fixes this by letting the mask vary per subnet, based on how many bits that specific subnet needs, literally subnetting a subnet. Golden rule, worth repeating. Always size the largest subnet first, then keep subnetting the leftover space for progressively smaller needs, always starting on a valid bit boundary. Worked example continuing from slide 35. Take the unused 8th/27 subnet, 192.168.20.224/27, 5 host bits, and subnet it further just for the 3 WAN links. Since each link needs exactly 2 hosts, solve 2 minus 2 equals 2, meaning only 2 host bits are needed. Borrow 3 more bits from the 5 available. New prefix, /27 plus 3 equals /30. Result, 8 tiny /30 subnets, 3 of which get assigned to the actual WAN links. Complete VLSM scheme for 192.168.20.0/24 shown in the table. 427 subnets sized for the LANs, buildings A through D, 18 to 28 hosts each, plus 330 subnets for the R1, R2, R2, R3, and R3, R4 WAN links. This is what a finished VLSM design actually looks like end-to-end, worth having students trace every address back to how it was derived. The VLSM golden rule, worth its own slide. Biggest first, always. Sort every subnet requirement, from largest host count to smallest, before doing any math. Then allocate the biggest need first, using the most efficient available block. Working smallest to largest is the #1 cause of VLSM mistakes. You'll box yourself into a corner and run out of clean bit boundaries for the bigger subnets still waiting. Before subnetting anything, develop a complete addressing scheme for the whole network. How many subnets, hosts per subnet, which devices go where, and which parts use private versus public addressing. Study both intranet and DMZ together. Address conservation matters most in the DMZ, where public space is limited. The intranet has much more room thanks to blocks like 10.0.0.0/8. A good scheme always leaves room for growth. No single right way to organize subnets. 3 common strategies previewed earlier now get their full names, shown on screen. By location, 1 subnet per building, floor, or site. By group/function, 1 per department, administration, HR, engineering. Or by device type, a subnet just for printers, another just for servers. Pick whichever makes the network easiest to manage, secure, and troubleshoot. Different device types get different addressing approaches, shown in the table. End-user clients get dynamic DHCP addressing, less admin burden, supports mobile transient users. Servers and peripherals get static addressing, predictable, consistent. Internet-facing servers get static public addresses, often via NAT. Intermediary devices and gateways get static addressing too, since predictability matters for management and monitoring. Close the module walking each bullet. Network/host split found via logical AND, the network/broadcast/usable range structure of every subnet, Unicast/broadcast/multicast address patterns, private space and NAT, the 2 to the power of n and 2 formulas driving all subnetting, VLSM sizing the largest need first to avoid waste, and good address planning by location, function, or device type. This module ties together everything from Module 5's binary work through Module 8's addressing.